Welcome to today's online training, RFEM for students, part 4, Introduction to Steel Design. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software, more for the technical marketing. Yeah, for example, the Dlubal website, the German and English webinars, new features, customer projects, and so on. I will be the moderator and presenter today, and I will be supported by my colleague Sandy Matula, but she can introduce herself.
Hi, my name is Sandy. I am responsible for the customer support, and today I will answer your questions.
Okay, thank you, Sandy, for your introduction. Then we can switch off our webcams that the attendees can see the full screen. I say something about how to ask questions. You can show that control panel with that arrow here, and then you can enter a question here, and Sandy will answer you. Okay, then we come to that slide, the training series. Maybe you participated the first 3 trainings. If not, it's not a problem. Today, there is part 4, Introduction to Steel Design. And that's the content today. At first, I say something about the theoretical background. Then we turn to an introductory example, a 2-span beam. Then the next part or next point is imperfections. Then stability proofs in the ultimate limit state. And then we turn to a second example, a flat hull frame. Okay, before we start, I would like to ask you something with a survey. Just a moment. So I started. Yeah, just click on the point that it's valid for you. The question is, how much experience do you have with design according to Eurocode 3 and steel design in RFEM? Just click on it. Okay, then I close the survey. Last chance to select something. Okay, I close it and show it. Okay, the most of you clicked, it's new or quite new for me. Yeah, that's why you are here. I hope I can learn you something about the steel design. Yeah, and I will start now. So, okay. At first, I say something about the products for the design according to EC3. Yeah, the most important add-on is the steel design add-on. And with that add-on, you can design steel members according to international standards like Eurocode, AISC, and so on. We use or we calculate or design according to Eurocode today. Then there's the add-on torsional warping. With that add-on, you can consider the 7th degree of freedom, and the torsional warping. Then steel joints. With that add-on, you can analyze steel joints based on the finite element method. Then there's the cross-section program, R-section. Then the add-on structure stability. We use that add-on in the second example. Then there's the add-on nonlinear material behavior. You can, for example, consider a plastic design of steel plates or so on and so on. And then there's the add-on stress strain analysis. Okay, then a little insight into the whole safety concept in steel construction. The actions should always be smaller than the resistance. Those are the actions. This is the resistance. And in addition, we have certain coefficients that we have to take into account depending on what type of proof is used. You can see the different coefficients here. And those are the coefficients for the German national annex. And you can see there is for the stability analysis another coefficient, a safety coefficient. But if you select the German national annex, for example, or another national annex, this coefficient is considered automatically from the program. It's automatically higher. So, okay, then the next slide. Elastic or plastic global analysis. Whether an elastic or plastic calculation is possible always depends on the cross-section classes. There are 4 cross-section classes. The first cross-section class, there's a high rotational capacity, and this allows a plastic structure calculation. Now, for example, you can consider plastic hinges, but it's not so often used in the practice. And the cross-section resistance can be applied plastically. Cross-section class 2, where is a low rotation capacity, this allows an elastic structure calculation. And as with cross-section class 1, a cross-sectional resistance can also be applied plastically. The first and the second cross-section class, where you can consider a plastic cross-section resistance. Then cross-section class 3 and 4 allow an elastic structure analysis, and the cross-sectional resistance can only be applied elastically. For cross-section class 4, only a reduced cross-section resistance, the effective cross-section. Okay, what's important to you in the practice? Mostly you do an elastic global analysis. It's not very often that one consider, for example, plastic hinges. And what's important to you is that the first 2 cross-section classes can be calculated plastically or designed plastically with the cross-section resistance plastic, and the cross-section class 3 and 4, where can the cross-sectional resistance can only be applied elastically. Okay, then I start the next survey. The question is, for which cross-section classes may only an elastic cross-section resistance be applied? Just select what you think what is correct. I wait some seconds, and Now I close the survey. So, yeah, the most of you selected or choose the right answer. I showed the slide again. Yeah, cross-section classes 3 and 4. Yeah, can you consider the cross-section resistance elastic? Okay, then we turn to the next slide. That's the first example, the two-span beam. Now with a field length of 12 meters, 12 meters right, left and 12 meters right. A beam IPE 550, steel S235, a self-weight load case and a load case with an imposed load. And we will calculate or do a cross-section classification, cross-section design checks. Yeah, the difference between the elastic and plastic cross-section resistance. We take a look at the design checks, elastic and elastic plastic. Okay, I turn to RFEM. That's the second example. It's already prepared. But for the first example, I model the complete model or the complete structure. File new. So I enter 0, 1, 2 span beam. Okay, then type of model 2D is sufficient. We consider only members, but you can also select surfaces, that doesn't matter. And we select the steel design add-on. Okay, then we need to select the standards. You can see there are, for the load cases classification and the steel design, different international standards. We select the Eurocode, and for today we are in Germany here, we select the German National Annex. Okay. We don't use the load wizards, but we use the load case classification and the steel design. We leave the dialog with OK. So I turn to the view -y. Move it a little bit. So the grid is 1 meter. I leave that. If you want to change that, you can click on this here at the bottom, display grid, right click and then edit. And you can change the space for the grid points. So I start with the beam, left above, new single member. I need to define a section, create new section. I turn to the library, left above, an I-beam. If I am too quick for you, that doesn't matter. There is a recording. When you want to enter the structure by yourself, you can use the recording and the finished models. In the next days, you will get an email with the recording and the models and so on, the PowerPoint slides. Just take a look what I show. That's sufficient. Okay, I select IPE 550 and right at the bottom I open the material library and I select European Union, steel, carbon steel. There are a lot of steel materials. I use the steel material S235. Okay, you can see now the color is blue. That's okay. So I create a member with a length of 24 meters, and I divide the member in the middle with right click, members, and divide member and intermediate nodes. One intermediate nodes, and that I create the node without dividing the member. I select this option here, create on member nodes without dividing member. Okay, there's the node. So then I create the supports. Here left above, assign nodal support. So I press the edit button to take a look if all is okay. Yes, we support in an X direction and in Z direction. Okay, and this node is quite a little bit small. With a right click, I can increase the size of the support. Okay, that's enough. So next support, I select the second support and press the edit button. Yeah, we don't want to fix the rotation for the support, and we deselect the fixing in X direction. We only want to support the member in Z direction. Okay. So that's all for the model. I create the loads. There's a self-weight load case. I select here edit active load case. The self-weight load case is automatically created for every model. So, and you can see also the self-weight of the structure is activated. Yeah, that's correct in our case. So, and above, here, this button, new member load. And our load should be a force, uniform. You can see there are different options. And the load direction should be in Z direction, in this direction. So, and the load magnitude should be 8 kilonewton per meter. Okay. So then I create a new load case with that button. I call it imposed load. And I select the action category, not permanent, but imposed loads. Okay. Okay. Then I have to create the load for this load case, new member load, and this time 12 kilonewton per meter. Okay. That's all for the model and for the loads. I open the load cases and combinations dialog again, this time over the navigator data with a right click. Load cases and combinations. Where are the base data? Now, at the beginning, we selected the standard group Eurocode and the German national annex, and we activated the combination wizard. Those are my two load cases. We've got only two actions. that's quite important when you have, for example, 4 wind load cases. Then there's only one action for the wind load cases, and you can combine in the load combinations either wind in -x or wind in +x and so on. Okay. So then there are the design situations. We would like to design only according to ultimate limit state. That's why I delete the design situations for the serviceability limit state. And what's important, we need to activate the steel design. So, and there are only 2 load combinations. And if I turn back to the design situations and to the overview, where are assigned these 2 load combinations for the design situation ultimate limit state design. So then we can calculate also the steel design. At first, we take a look at the internal forces and the navigator results on the left side. The VZ, for example, I can also select only the maximum values, not minimum and maximum. So BZ and MY. So, and then we can go to the table at the bottom and to the steel design. An error is displayed after the calculation. This is because we haven't made any steel design settings yet. We are only interested in the cross-section verification here. Therefore, we change to the table design ratios and members. So there's the section proof for shear and for bending. And you can see a plastic design were done for the program. So if I select the line and press this button, design check details, this dialog is opened. Students request for a detailed presentation of the proofs is now possible. You can see the equations and where you can find it in the standard. Okay, then cross-section classification. You can see where is the cross-section is classified in class 1. That's why a plastic design is possible. So we can also take a look at the result diagram, the design ratio, the stresses. That's the stress in the middle, or over the middle support, and there's tension at the top and compression at the bottom of the cross section. So okay, that's all. Can I show also maybe the cross section information, the stress points, the different sub panels for the cross section classification, the C to T parts. Okay, that's all. And the same, you can also, if you want to check the proof for the shear, you can either press that button or double click on the line. And you can see the equations from the standard. Okay, now we don't want to do a plastic, but an elastic design. How to do that? I turn left at the bottom to the navigator data. Then I open the steel design folder and the ultimate configurations. And I double click on it. Yeah, and then I can, for example, uncheck the stability design. Then this error message don't appear, but doesn't matter. I select that button here. Elastic design also for class 1 and class 2 sections. Yeah, it's allowed to do a plastic design for class 1 and 2, but yeah, in this case, we would like to do an elastic design also for the cross-section class 1. In our case, the cross-section is cross-section class 1. Okay, we calculate or rerun the steel design again. And I select design ratios and members. I remember we had a design ratio for the plastic design of 84%, and now we have got 94%, yeah, because we do an elastic design. And if I double click on it, I can see the equation. Okay, what you can hold in your mind is that we can do every time an elastic design. We can consider the elastic cross-section resistance. That's what we did in the second step, in that step here. Yeah, so we have now learned how to carry out a cross-section check and how to take the elastic and plastic design into account. Yeah, at first the plastic design, in the second step the elastic design, because elastic design is allowed for all cross sections. And in addition, we now know how to display the design formulas and compare them with our own manual calculation. Okay, I start the last survey for today. So the question is, the elastic method applies to all cross-section shapes and can therefore always be used. Is that right or is that incorrect? So I wait 3 seconds and I close the survey. Yeah, the right answer is the first answer, right? Most of you have it wrong. That's why I showed the PowerPoint slide again. So, yeah, for the cross-section classes 1 and 2, whereas you can consider a plastic cross-section resistance. That's what we did in the first step. The program detected that the cross-section is in class 1, and that's why the program did consider the cross-section resistance plastic. But we said we would like to consider an elastic cross-section resistance. And the elastic cross-section resistance is, well, you can apply it for all cross-section classes. That's what we did in the second step. Okay, then we turn to the next topic for today: effects of deformed geometry of the structure. In the first training course, Introduction to Member Design, it was learned how the results can differ between the calculation according to the first order theory and the geometrical linear analysis and the second order theory. The geometrical linear analysis is an equilibrium formation on the undeformed system, and the second order analysis is an equilibrium formation on the deformed system. In this example of the cantilever column, this effect can be seen very well on the basis of a slender. That's the slender and a compact cross-section. In the case of the slender column, the increase in the bending moment at the foot point is much larger than in the case of the compact column. If one calculates according to the second order theory. And there's no difference when you apply the geometrical linear analysis. So, and for steel construction, there's a value that defines when a structure should be calculated geometrical linear or according to the second order analysis. If the critical load factor alpha crit is less than 10, the system must be calculated according to the second order analysis. And in this case is written in that way: alpha crit larger than 10, then it's sufficient to apply the geometrical linear analysis for an elastic design. And if you want to do a plastic design, the alpha crit must be, if that is larger than 15, then you can also design according to the geometrical linear analysis. Okay. So then the next point is the equivalent geometric imperfections. Imperfections are also closely related to this topic. Here we have the imperfections in Eurocode 3, and these are generally grouped together as an equivalent geometric imperfections. Maybe first of all, what are imperfections anyway? Imperfections are production-related deviations in the model geometry and or in the material properties. On the one hand, there can be real misalignments in classic hall constructions or tolerances in production, especially when rolled sections are used. And these imperfections can be summarized as equivalent geometric imperfections. On the left side of the graphic, you can see the initial sway, the global imperfection that can be applied to the structure. And if individual components are to be examined more closely, where is the local equivalent imperfection, for example, over an initial bow imperfection. And this depends on the selected profile, the yield point, the buckling curves and the proof method. Yeah, and these two variants are possibly of the equivalent geometric imperfections. Another alternative is pre-deformation, which can be calculated with the help of stability analysis. The respective governing eigenmode is scaled and applied as an imperfection. That's not so often used, but it's possible. What you often use is the initial sway imperfection or the initial bow imperfection, or both. That can you see in a later slide. When designing steel in RFEM, 3 different stability analyses are carried out. On the left side, there's the classic flexural buckling as a lateral deflection. Then in the middle, you can see the torsional buckling in a pure tension. And on the right side, the lateral torsional buckling as a combination of the two previous proofs. Okay, methods for stability analysis. There are 3 methods. Method A, you have to apply a global and local imperfection, and the structure analysis should be done with the second order analysis. And then you can do the cross-section design checks with the internal forces. Method B, global imperfection, means only this initial sway imperfection. So, and then the structure analysis according to second order analysis. And what's quite important, you have to consider the buckling length by the member length, not with a factor. SK is equal length. Okay, then method C, structure analysis according to geometrical linear analysis on the ideal structure, but in that case with the real buckling length. Okay. Yeah, and important to method C is the structural component design can be carried out for flexible buckling with the internal forces according to the geometrical linear analysis, which were determined on the ideal structure without the use of imperfections. But in that case, here for the frame, only for the columns. Because by considering the system buckling lengths, the moment agrees according to the second order analysis, and the effect of the equivalent imperfections are already taken into account. But that's also a sentence in the Eurocode. For the design of the lateral torsional buckling, the application of the second order analysis is also required with that method. Now, if you want to do a lateral torsional buckling design for the horizontal beam, then you need also for this method to calculate according to second order analysis. We show also this method because we know in the studium you have to define the real buckling lengths, and I would like to show that method that you can see how to determine the buckling lengths. And in the next example I will also show the method B. What's for the practical use, it's often used in the praxis. And also method A, and method C, seldom or more in the studium. Okay, that's the flat house frame, the second example. You could see it's all already defined in RFEM. Also material S235. You can see the different lengths, 12 meters, 15 meters, 12 meters. That's the frame. And then where are columns, and those are hinged columns on the left side and on the right side. And you can see a hinge, a hinge, a hinge, a hinge. Okay. So that's all for the introduction. Okay, snow load case, I can show that in the program as well. And the tasks for this example is to apply imperfections, and we will do a stability analysis according to method B and method C. I start with method C without imperfections, and then I turn to method B and where are the imperfections necessary. Now we can turn back to the slide. That's with the determination of the buckling lengths, and that's and without imperfections, and method B with imperfections. Okay, so then I turn to the program, to the predefined example. So that's the construction self-weight load case, then a snow load case with loads, for example, from purlins, and a wind load case. Wind in X direction with wind pressure and wind suction. Left above, I go to or turn to the base data, a 2D model, and we use the add-ons structure, stability, and the steel design add-on. And we select the standards, Eurocode, and the German National Annex. Okay, so yeah, and we use the add-on structure stability to check whether we are allowed to determine the internal forces according to the geometrical linear or second order analysis. That's why we turn to the load cases and combinations. And I go directly to the design situations. I select the geometrical linear analysis, and I edit that, and I activate the stability analysis. Okay, and I run the calculation. So and after the calculation, we see the minimum critical load factor, 6.05 for the design situation, and 6 is smaller than 10. Yeah, we need to do a stability design by using the second order analysis. Yeah, but what I already mentioned, for the stability design using the classic equivalent bar method, means method C, the internal forces can be calculated according to geometrical linear analyzing, and yeah, buckling lengths must be assigned to the columns. Yeah, but for the design of the lateral torsional buckling, the application of the second order analysis is also required with this method. That's why I switched to the second order analysis. For the columns, yeah, we consider then the effect, yeah, twice. Yeah, one time with the second order analysis and with the real buckling length. But we need to do the second order or need to apply the second order analysis because of the horizontal beam and the lateral torsional buckling. So, but let's take a look at first to the buckling length. I turn to the stability analysis. So, and then results by member. It was combination number 3. So, and then I can see the effective lengths and critical loads by member. So this column has an effective length factor of 3. This column, yeah, we apply also 3 for this column. And for the left and the right column, 1.72. Okay. So I turn back to the design situation and we run, or we use the second order analysis. Okay, that's okay. So, and now we apply we define the effective lengths, or we assign them to the columns. I select the inner columns, then I do a right click, members, edit, and I turn to the design configurations and design types, and I define effective lengths. So I would like to mention that you can also import the buckling length from the stability analysis. Now we don't do that in that example. So then nodal supports and effective lengths. I define the effective length of 3 meter, of the effective length factor of 3. Okay. Okay. Then I select the left and the right column. I press the control key. You can see the plus sign. I would like to consider or select both columns. Then right click, members, edit. The same procedure, design types, effective lengths, and 1.72. Okay. And you can display the effective lengths. Then we go to the navigate to display. Then types for steel design, and I select member effective lengths. And you can see the factor 3 and 1.72. So then I select the inner horizontal beam by right click, members, edit, then design types, effective lengths. I create a new effective length. So this time we would like to consider the horizontal supports, for example, by purlins. That's why I press this button here, select member or member set. I select this member, and the program will detect all these nodes here. Okay, you can see that here, and we would like to fix it in horizontal direction. And I would like to consider that the upper flange is supported. The purlins lay over the horizontal beam, or the okay. That's why I select all these lines here, and I define eccentricity type at upper flange. Okay, I can leave the dialog, and you can see the supports. Gable support at the beginning and at the end, and for the inner nodes there are only a horizontal support at the upper flange by the purlins. So okay, we need to do the same for the left horizontal beam and the right one. I select both with the Control key. Then members, edit. And I select the same effective length as for the middle horizontal beam, and you can see the program detects automatically that there are only 3 nodes. You can see 3 nodes are supported and 4 nodes. Okay, then we can run the calculation. I turn to Steel Design and press this button, Show Results, and the calculation starts. So the calculation is done. We have a maximum design ratio of 84%, stability, bending, and buckling about principal axis. So I can double click on it, and you can see the design checks, the equations, and where you can find it in the standard. Okay, this was the classic structural component design, method C without imperfections, but effective member lengths. Now we want to examine the model using the approach of global imperfections and the structural component design method B. I turn back to the PowerPoint. We did method C with the effective member lengths and without imperfections. And now we define imperfections, and I delete the effective member lengths for the columns. We say, or we consider SK equal member length. Okay, I turn back to the program. Left at the bottom, I go to turn to the navigator data, then types for the steel design, effective length, or let me save that state, save as, out results. So without imperfections. Okay, I overwrite it. So, and now I delete the effective member lengths for, or the buckling lengths for the columns. Delete. Okay. And in the second step, I need to define imperfections. So above here, that button, new member imperfection. I have to create an imperfection case in the first step. imp x. We have got imperfections and imperfection cases. You can consider more imperfections in one case. That's why we have imperfection cases and imperfections. That's the case, okay? And now we create the imperfection for that imperfection case. We define an initial way. Define type is Eurocode 3. In the imperfection direction is set, in the strong axis. Then the basic value is 200. I can measure the structure height. (8 meters). Number of columns in one row, those are 4. Yeah, and the reduction factors are calculated automatically. Okay, and I need to assign it to all 4 columns. And to display it, I have to press this button above, Show Imperfections. So, and now we can run the calculation. Or before I do that, I take a look at in the design situation. Second order analysis or second order analysis. And it must be checked that the program considers the imperfection cases. Okay, now we can calculate all. So we go directly to the steel design. So design ratios on members. Yeah, and you can see the design ratios. With the method C, we had a design ratio of 84%. Now we've got 86%. That's quite similar, different methods. Okay, yeah, that should be all for today. You learned in the second example how you can apply the method C in the first step, and then with imperfections with the method B in the second step. Yeah, and as I already mentioned, you will get an email in the next days with your attendee certificate. And then you can watch the recording if you want. You can download the models that I saved. Yeah, I hope you could learn a little bit in this online training. And yeah, maybe last wish when you leave the webinar, where is a small survey. Take the time. It takes you only 1 minute, I think. You can score the webinar, for example. Note that the worst score is 1 and the best score is 5. Yeah, I wish you a nice rest of the day and much success for your studium. Yeah, and take care. Bye.